Okay, guys, I guess that I need to finish this lecture. I thought I had already done it. Um, this is going to be the angular momentum of rigid bodies and the conservation of angular momentum. Real quick, review that remember that L is our angular momentum, and that equals our radius vector crossed with our momentum vector, and we can find the value of this with our L also equals our rotational inertia times our angular velocity. All right, and this follows that through our analogous variables that our tau, our net torque, is equal to, since our net torque is equal to I alpha, this is the same thing as dl dt, or it's the time derivative of our momentum, which is analogous to our force, mass times acceleration, equaling our dp dt as Newton's original law. So now we get to the we're talking about analogous variables and the conservation of angular momentum. And so let's have for us an axis here. All right, and we have this rigid body with a mass out here that is at a position r(I) from the center. And as this thing rotates, it has a linear velocity of vi, and this little piece right here is a mass I. And as this rotates around, okay, this is the closest thing that I have to a circle. As this rotates around, this particular piece, we know the angular momentum of this is going to be the angular momentum of that particular particle is going to be the radius I crossed with its momentum vector I. Okay, but we know that this equals, because of we know what momentum is, that it's just going to be this winds up being Ri and then mass times velocity for the momentum. So it's Ri mi vi for our momentum. Now, and we know this because our velocity also equals Ri omega here. And so notice that there's no I for the omega, that there's no individual piece, that this particular piece doesn't have an omega that's different from any others, because this entire piece is rotating with the same angular velocity, that it's all going to sweep out the same d theta dt as it goes around. So it doesn't matter where this particle is, or for its velocity. It's always going to be its radius times whatever angular velocity it has. So that can go in here, and we wind up with our Li equaling the radius for that times the mass for that thing times the radius again times its angular velocity. Well, this conveniently, if we regroup this to have those guys go together, then this is going to become mi Ri squared omega, and lo and behold, this is our rotational inertia. And so what can we do? We can take the sum of all of these, or we can do it from here. So we take the sum of all of our angular momenta, and that's going to equal the sum as I goes from 1 to infinity of all the little pieces of mi r squared I omega, and this becomes L, just the total L, not I, just L, equals I omega, and that's our, that's our the quick review of our angular momentum. Now, okay, we can go on from here, and if we know that, okay, this is our angular momentum, and then if we do, if we want to see how this changes, then we take our L. I'm going to move it over here a little bit. Our L, if this equals our I omega, then if we take dl dt, of that vector, it's going to equal d dt of I omega, which winds up equaling I d omega dt plus di dt times omega. Well, very rarely does our moment of inertia change with time as we're moving. This happens with fluids and with, if we're dealing with massive numbers of particles or gases or that sort of thing, then we start having this term. But you are not going to see that. So this is always going to go to 0 for us. And so we get I equals d omega dt. But what, of course, is I omega? Is omega dt is just alpha. So we wind up getting dl dt, the time derivative of our angular momentum, is going to equal I alpha, which equals our net torque, just like in linear, just like with our linear analogs over here. So, right. So this is our angular momentum part. Now, if there is no net torque, and I'm actually going to write this one out because I want to make sure that you've got this, guys. If there is no net torque, if no net torque, okay, if there's no net torque, then the angular momentum is conserved. All right, if there is no outward force, if there's no force on the on your rotating, or sorry, if there's no rotational force, if there's no torque on your object, then all of the angular momentum will be conserved, and there's some really cool demonstrations to deal with this. The egg was one of them. We did it with Corey in class when we gave him the masses and had him spin on the spinning wheel, and as he brought the masses in, he started to spin more because his I reduced, and well, we're going to get into that here in a sec. So this means that our initial angular momentum must equal our final angular momentum, and we see this all the time. If we spin a top, okay, and I've actually got one here that I can use for you guys if I can pull it out and not disturb other things. All right, if we take the top and we spin it, hopefully it'll stay put for us. It looks like it wants to slide down. No, this is not level, so maybe if I put it, maybe if I move it over here. I just don't want to stay on the, doesn't want to stay on the paper. It always wants to slide off. So maybe if I do this, maybe if I give it a, okay. This is happening because I've got I obviously have a slant to the table of a slant on this table, which I would prefer to not have. But what keeps us upright is the conservation of angular momentum. That if this alters its, okay, so think about, actually let's spin it. So I'm giving it a clockwise spin. I'm going to spin like that because I'm right-handed, and right-handed people usually give things clockwise spin. The angular vector, so let's think about what the angular vector of our the vector of our angular momentum is here. So if I give it a clockwise spin, that means we have our torque is pointing this way, and our radius is pointing that way. So if we go R cross F, then we give it a, okay, so it's R cross F, and we take our right hand, we have to turn our fingers into the direction of the force, which makes it go down into the paper, is the direction of our angular momentum. And so if this top tilts at all, it starts to rotate and it starts to adjust in order to maintain its angular momentum. And so any kind of adjustment that you feel, I wish I had a platform where I could create a balance. So any kind of adjustment to the direction of the axis results in a motion of the motion of the top, and this is called precession. If I had a really good one, a great example of it, if you guys have seen the movie Inception, the reason that, now I'm going to blow some minds here. I may even, spoiler alert here if you haven't seen Inception. The reason, the way that Leonardo DiCaprio's character Cobb is able to remember that he is in a dream, not in real life, is he has this top, and it is his own personal talisman, and nobody else knows he has it, unless people he trusts. And he spins the top, and if it stays spinning perfectly forever, then he knows he's in a dream, because that's how he tells that that things are distorted. The reality is distorted because the top should be precessing. If it ever tilts over, then he's back in real life, and that actually plays a pretty important part to the movie. So I don't want to go too much further with that. The other thing is the Earth happens to spin on its axis, and so let's. Okay, the Earth actually spins on a tilt that is 23.5 degrees. (23.5 degrees) off of vertical. And if we have our sun that is blazing down, okay, I'm going to draw the kindergarten sun over here. Okay, it's blazing down with light. The sun, at any particular part of the year, so in fact, let me draw the sun in the middle here. It's really far away, that's why I'm drawing it small. But it's blazing rays that way, and it's going to blaze rays that way in just a minute. But the rays come in, and they hit directly onto the Earth like this, but the equator of the Earth isn't right where it's hitting like it should be. It's perpendicular, of course, to the axis of rotation, so it's circumferential like that. Well, the highest point up here, I way over exaggerated this, but there's a circle up here that represents the highest point that receives vertical rays from the sun, and then there's another one down here. There's another one down here. There's another circle on the globe that receives, this is way too far up, it's down here. It's the highest point that receives vertical rays of the sun, and this is called a tropic. And these are both the tropics. Tropic of Cancer and Tropic of Capricorn are the two tropics, and it is this region that receives the bulk of the sun. Because when the Earth gets to the other side, over here, the conservation of angular momentum says that it's still tilted in that direction, even though the Earth goes around the sun. Okay, it doesn't stay one end tilted and the other end not, and so the sun's rays now hit the lower hemisphere. Oh, wrong color. The sun's rays now hit the southern hemisphere with the same force that they hit the northern hemisphere over here, and that creates summer for the southern hemisphere. But it also hits the northern hemisphere, but at a much more oblique angle, and that creates winter for us, and that's where we are in our season right now. So, that's also so the Earth obeys its angular momentum also as it tilts on its axis. Now, the one that you guys may have seen is if we have a draw this best I can with my foot, and we have a skater who's got another skate here. Okay, skaters usually have boots on, and their hands are way out, and they're spinning like this around on the ice. And with with their arms out, this has a large initial angular momentum when they're spinning. Okay? But and you've seen this all the time, you've seen ice skaters, when they bring their arms in, so let's draw another one. Get another skate. Okay, and they bring their one leg here, and they kind of curl it around. Okay, and their arms are they bring their arms beside their body. What happens to their moment of inertia? Well, the masses are no longer far out away from the center of the body, they're very close in, and so we now have this final moment of inertia. And because this one is greater than that one, look what happens to our conservation of momentum. That if we have our initial L equals I omega initial omega, okay, and that's also going to equal, because there's no other forces, let's assume that the friction is negligible on the ice, we have I F omega F. Well, what's our final velocity going to be if we start pulling in our arms and our legs to create a smaller moment? Well, our final angular velocity is going to equal I initial over I final omega initial. And if this is larger than that, then our angular velocity is going to increase. Or if you start spinning quite tightly, and the way they get out of this spin is they kick their leg out and they spread their arms out, and they give you another look. I'm going to draw it kind of smaller here. But then they kick out of it with go this way, and then they kick their legs out way back. And in fact, the head is in the wrong place. They actually lean out like this, and they have an arm back, and they have another arm back, and their head's out here, and they spin out, and they really slow down by tilting their whole body over their leg, and that allows them to slow down and curl out of their spin. Which is really just fascinating physics to watch. If you watch skating from a physics standpoint, I don't really watch it a whole lot from a sporting standpoint, although what they do is incredibly athletic. But I love watching it from the physics standpoint and watching the trails on the ice. Okay, so real quick, let's go over analogous variables here. We have a momentum now. If we have a momentum that equals mass times velocity, and with it goes a angular momentum that equals the rotational mass times the rotational velocity. Okay, then we also have a force, and that force equals mass times acceleration, and we have a torque, and that torque that equals rotational mass times rotational acceleration. If the net force on an object equals 0, then we have the conservation of linear momentum. If the net torque equals 0, then our angular momentum is conserved. And these concepts are crucial for some of the questions that you're going to see on your test. So there it is. That's the lost lecture, and I'm going to put it up right now so that you guys have it and you can finish your studies for Unit 5. And we'll see you guys in class.